Hey everybody, welcome back to chemistry, and we're continuing on through chapter 6, and we're getting to a concept called heat capacity. So let me define it. It is the amount of heat needed to raise the temperature of a piece of matter up 1 degree Celsius. So let's take an everyday example. So let's say you have an empty copper pot, and let's say you put it onto a stove burner, and let's say you turn on the burner. So I think you know from experience that the copper pot will get pretty hot pretty quickly. In other words, it didn't take much heat to get the copper pot to maybe go up 1 degree Celsius. Now on the other hand, let's say you took that same copper pot and filled it up with water and you put it onto the stove burner. There it might be a little bit of a different experience, right? To get the copper pot and the water to go up even a little bit of temperature is going to require a lot more heat. So I think what you can see is in this example, water is able to absorb a lot of heat without having much of a temperature change. And if that's the case, water is said to have a very high heat capacity. On the other hand, the copper by itself, just the copper by itself, it really cannot accept a lot of heat before it gets very hot. If that is the case, then you would say the copper by itself has a very low heat capacity. Now, what I need to do is talk about two forms of heat capacity. One is called the general heat capacity, and we're going to compare it to something called specific heat capacity. So to really sort of understand these, what I want to do is sort of give sort of a simple example here. Okay, so let's say you're at home and you have some burners on a stove, and let's say right now the burners are off. Now let's say that you happen to have a piece of copper, and you get a mass of it, and it's 10.0 grams, and so this is copper. And let's say you have that piece on this burner, but let's say you have another piece, a much larger piece of copper on this burner. This is 5 times the mass. This is 50.0 grams of copper, and you have it on this burner. And let's say initially you measure what the temperature of these blocks are on the copper before you turn on the burner. So the initial temperature here, let's say, is 24.00 degrees Celsius. And same thing with this one here. Initial temperature, 24.00 degrees Celsius. Okay, now let's say that you turn both burners on. So you're turning on the burner, so the burner now is warming up and it's getting hot. And so you kind of know that what will happen is that heat will leave the burner and go into the copper block. So the symbol for heat is Q. Now let's say, and with the small one here, you add the heat to the copper block, and let's say you stop the experiment when the copper block gets to be 25 degrees Celsius. Now, let's say you were able to somehow measure the amount of heat that was able to go into the block. And what you would find is for the small copper block, you would find that 3.85 joules of heat entered that block to raise it by 1 degree Celsius. Okay, now let's say you did the same experiment here, but with a larger block. And so let's say you turn on the burner, and then this time heat goes into the larger block. But maybe you probably notice you're going to have to wait a little bit more for it to get up to 25 degrees Celsius, right? Because it needs more heat because it's a larger block to get up to the same temperature. So let's say the final temperature here is at 25.00 degrees Celsius, and you stop the experiment, and you're able to measure the amount of heat that went into this large block. So again, I think you can probably see here, we both have copper in each case, but you might expect that the larger block is probably going to need a lot more heat to go up 1 degree than the smaller block. That is true. And so I think if you actually measured that amount, then the heat here would be 19.25 joules. Okay, so now what I want to do is I want to calculate a general heat capacity for the small block and for the large block. So how do I do that? I use this formula here. So the general heat capacity is symbolized by a large capital C, is equal to Q, which is the heat, which is measured in joules, and then the temperature change, which is measured in degrees Celsius. Okay, So let's go ahead and calculate the general heat capacity of the small block. So this is what you do, is it's going to be large C is equal to Q, and so for the small block was 3.85 joules, and then we're going to divide it by the temperature change. Well, going from 25 from 24, that is a temperature change of 1.00 degrees Celsius, so we divide this by 1.00 degrees Celsius, and you can see for the small block, the heat capacity is 3.85 joules per degree Celsius. And so those are good units for the general heat capacity. Okay, so now let's go ahead and calculate the general heat capacity for the large block. Okay, so here it's going to be the general heat capacity is equal to heat that entered the large block, which is more because it was more copper, right? 19.25 joules. Divided by the temperature change, which was here, same thing here. It was 1 degree Celsius. And here you can sort of divide those two numbers and see that the general heat capacity of the large block is 19.25 joules degrees Celsius. Okay. So one thing you can see is that if we have the same material, if we have more of it, then we're going to have a greater general heat capacity. So I think one thing you can immediately see is that general heat capacity is an extensive property. The more material we have, the greater the value here of the general heat capacity. So the general heat capacity depends on the amount of matter. Okay. So now let's move on to a slightly different calculation. Now we're going to calculate the specific heat capacity. And so I have the formula here. It's modified a little bit. Here, specific heat capacity, that's represented by a little c, is going to be equal to heat, Q, in joules, and it's going to be divided by m of the mass of the material you're heating up. So this is mass. And its units here will be in grams, and then delta T will be in degrees Celsius. Okay, so now we've calculated the general heat capacity of these two blocks. So let's calculate the specific heat capacity and see what those values are. So for the small block, it's going to be little c is going to be equal to the heat, which was 3.85 joules, divided by the mass of the block, which is 10.0 grams, and then in the denominator, this is multiplied by the temperature change, which is 1.00 degrees Celsius. And so the specific heat capacity, you work it out, for this block is 0.385, and the units are joules, and you'll see in the denominator there's grams degrees Celsius. So that's the specific heat capacity of the small block. Okay, let's do it for the large block. So here, specific heat capacity for the large block will take how much heat this large block absorbed, which is 19.25 joules, and we divide it by the mass of the large block, which is now 50 grams, and the temperature change, which is 1.00 degrees Celsius. Anyway, I think if you divide those numbers out, what you would get for the specific heat capacity of the large block is 0.385 joules per gram degrees Celsius. So this makes a very important point here, is that here with these two copper blocks, they have different masses, and if they have different masses, they will have different general heat capacities, but they will have the same specific heat capacity. So the reason why that is true is because it has to do with the formula. And so with the specific heat capacity included in the formula, you're dividing out the mass. And so here, this calculation is adjusted for the mass of the copper block. And therefore, the specific heat capacity will be the same no matter how much copper block you have. If that is the case, then it looks like while general heat capacity was an extensive property, because the specific heat capacity for copper is always 0.385 joules per gram degree Celsius. No matter how much copper you have, it is an intensive property. It will not vary no matter how much copper you have. And so here you can maybe imagine is that the specific heat capacity maybe is dependent on something else. It's dependent on the kind of matter you have. And so I want to go over to the computer and show you a slide here. So I'm going to the computer. So on this slide, what we have on the right here is we have a table of different kinds of matter, and you can see the values of the specific heat capacity that each matter has. Now, we were looking at copper here. So here is copper, and then what you can sort of see is the value of the specific heat capacity is 0.38. I calculated over my little problem 0.385, and it's joules per grams degrees Celsius. Now, as I was talking about before, if you're dealing with a piece of copper, it heats up quickly. So what does that mean? It means that you don't need a lot of heat to get a major temperature change. If that is the case for a piece of matter, then it's said to have a very low specific heat capacity. But you might remember in my earlier example, I was talking about water. So water, it takes forever to heat up water and to get it to a certain temperature, right? And so there you need a lot of heat absorbed by water to get its temperature raised by a certain amount. Therefore, water apparently has a much greater heat capacity. And in fact, you can sort of see that in the values of the table here. So while copper has a specific heat capacity of 0.385 grams degrees Celsius, liquid water has a specific heat capacity much greater. It is 10 times or more greater than the specific heat capacity of copper. So the value is 4.18. So this is a really good example of how the specific heat capacity really depends on the kind of matter. And so other things you might notice is that metals in general have low heat capacity. So iron's heat capacity is about the same as copper. Lead is actually less. So if you had a lead plate and you were heating it up, it would become very hot even more rapidly than the copper plate, because all the heat you're adding to the lead goes into raising its temperature at least more than the heat going into the copper plate will raise its temperature. So also you can see that there are other materials here. So for example, dry air here has a specific heat capacity that seems to be intermediate between that of the metals and that of water. Now what I want to do is go over some problems which involve heat capacity, and there are two equations that you'll have to be aware of to help you solve these problems. So one equation describes something called general heat capacity, and so the symbol for general heat capacity is a capital C. And so you can see here the equation that capital C, again the general heat capacity, is equal to heat divided by the temperature change, where the temperature change is going to be always the final temperature minus the initial temperature. Now, when you see a problem, sometimes they won't say general heat capacity, they may say just heat capacity. If you see that in a problem, that is a reference to general heat capacity and this particular equation here. Now, another possible problem you might see might involve something where you have to use or calculate a specific heat capacity. And so the symbol for specific heat capacity is little c. And so here is the equation here where little c is equal to Q, which is heat, divided by m times delta T. And so m is the mass. Delta T, again, is going to be the final temperature minus the initial temperature. Now, in some problems, you won't so much see the phrase specific heat capacity. Instead, you'll see the phrase specific heat, and that is in reference to the same thing and using this equation here. Okay, so let's go ahead and try some problems. And so let me read out question one. Question one reads as follows. You place a metal plate on a stove. The heat capacity of the metal plate is 4.2 joules per degree Celsius. How many joules do you need to raise the temperature from 50 degrees Celsius to 95 degrees Celsius? Okay, so let me go to the board and solve the problem. Okay, so when you're looking at a heat capacity of the problem, what you sort of first have to figure out is what formula to use. Do we want to use this formula on the left, which is for the general heat capacity, or do we want to use this formula on the right, which is for the specific heat capacity? So I see some information in this problem that suggests that what we want is the formula on the left. So let me tell you how I kind of figured that out. So one thing I can sort of see in this problem is that there's no involvement of mass. And so mass is usually involved with a problem with specific heat capacity, but here we have no involvement of mass, and so that's the sign we'll need the general heat capacity formula. Now another sign is I do see a value for heat capacity there. So here the units for heat capacity that I'm seeing are joules degrees Celsius. Now another possible unit you might see for heat capacity is joules over gram degrees Celsius. But we don't see this. This is for specific heat capacity. We do not see this. Instead, we see this, joules per degree Celsius. And so this is for general heat capacity. So it looks like the problem we are going to solve involves general heat capacity, and so we have to use this equation for it. So what I'm going to do is I'm just going to erase this formula for specific heat capacity. Okay, so let's try solving for problem 1 here. So we have, it looks like a heat capacity. It's given to us. So remember when they say heat capacity, that means the same thing as general heat capacity. So this is a capital C, is the heat capacity or general heat capacity. And the value is 4.2 joules over degrees Celsius. Okay. Now, we also have to assign Q and delta T. So in this problem, it says, how many joules do you need to raise the temperature of this metal up a certain amount of temperature? And so we're trying to find joules, and therefore we're trying to find heat. We are trying to find Q, so I'm going to put a question mark here. Now, are we given the temperature change? Not directly, but we can calculate it. And so you might remember that the temperature change is going to be equal to the final temperature minus the initial temperature. Okay, so let's go ahead and calculate this now. So the final temperature looks like it ends up at 95 degrees Celsius, so I'm going to write 95.0 degrees Celsius. And we subtract from it the initial temperature, which is 50.0 degrees Celsius. And so the temperature change is 45.0 degrees Celsius. Okay. So at this point, we have assigned C and we have assigned delta T. So we should be able to plug these numbers in and get Q. Before I do that, let me just go ahead and solve this equation for Q. So how do we do that? Well, we want to isolate Q, so it has to be alone on its side of the equal sign. And you can see there's a delta T here that we have to get rid of. So to get rid of the delta T, one thing you could do is you can multiply both sides of the equation by delta T like this. And so if you do that, what you can see is that the delta T's here cancel out. And so what we can do is rewrite what we have, which is Q is equal to capital C, which is the specific heat, times delta T. So that's how you pretty much solve the problem. So let me just go ahead and plug in the numbers. So Q is going to be the heat capacity, which is 4.2 joules per degree Celsius, times delta T, which is 45.0 degrees Celsius. And so one thing we can do is we can see if the appropriate units cancel out, leaving the ones we need our answer to be in. And so what you can see is degrees Celsius cancels out, joules does not cancel out, so we should get an answer in joules. And so the math would be just 4.2 times 45. And I think to correct number of significant figures, that would turn out to be 190 joules. Okay, so that's the first one. So let's move on to the second one. The second one reads as follows. How much heat in joules must be added to 7.50 times 10 to the 2 grams of an iron skillet to increase its temperature from 25 degrees Celsius to 300 degrees Celsius? The specific heat of iron is 0.451 joules per gram degree Celsius. Okay, so let me go to the board and solve this. Okay, so again, sort of the first thing you have to sort of figure out to do is figure out whether you need the formula for the general heat capacity or the specific heat capacity. So again, we have to sort of carefully read through the problem and see what hints there are as to the kind of problem it is. And so one thing that you'll notice in this problem that there is a mass. And so the mass is given to us, let me just write this here, it's 7.50 times 10 to the 2 grams, okay? It looks like there is a temperature change mentioned, so I'm going to write this here, delta T. And so you might remember is T final minus T initial. Let me just go ahead and work that out now. So in this problem, it looks like we're going from 25 degrees Celsius to 300 degrees Celsius. So what we want to do is take the final temperature, which is 300.0 degrees Celsius, and subtract from it the initial temperature, which is 25.0 degrees Celsius. And so this is going to be 275.0 degrees Celsius. Okay, now it looks like we are given a value of some kind of heat capacity. Now note it says specific heat. So just to remind you, when it mentions specific heat, that's the same thing as a specific heat capacity. So what a specific heat capacity is little c. So little c is equal to 0.451 joules per gram degrees Celsius. Now it looks like in this problem that we're trying to find how many joules of heat is added into this piece of metal. So we're trying to find the amount of heat, which is Q. Okay, so maybe you can sort of look at this list of variables here and you can sort of see probably which formula we want to use. We want to use the formula for specific heat capacity. And the reason is the formula for general heat capacity does not include mass, but the formula for specific heat capacity does. And so let me give you that formula. So it's going to be C is equal to Q over M times delta T. So I can put a times sign here if I want to, times delta T like that. Okay, so this is the correct formula. So now the tricky part is solving for Q. Okay, so there are a number of ways you can do that. So let me show you one way. Again, you sort of say to yourself, well, I need Q to be isolated on this side of the equal sign. So we need to get rid of the M times delta T. So what we can do is multiply both sides by M times delta T like this. And so you can do that. And if you do that, then M times delta T cancels out here. And so what do we have now? Now we have Q is equal to C, little c, times M times delta T. But you can also, usually you'll see it like this. Q is equal to C M delta T. So that's one way of writing it. Okay, so at this point, I think we can just go ahead and solve the problem. So we just plug in numbers. So Q is going to be equal to C, which is 0.451 joules over gram degrees Celsius times mass, which is 7.50 times 10 to the 2 grams, and then delta T, the temperature change, it looks like is 275.0 degrees Celsius, so 275.0 degrees Celsius. Okay, so let's just make sure that units cancel the way we hope, leaving the units we hope to find in the answer. So here's degrees Celsius, that cancels out with that here. And here's grams, they cancel out. And then joules here looks like it doesn't cancel out, so that's left in the answer, which is what we want. So I think if you go ahead and do the math and round to correct number of significant figures, you'll find the answer to be 9.30 times 10 to the 4 joules. Okay, so we got one more problem, so let me bring that up. Okay, a piece of unknown metal weighs 254 grams. When the metal piece absorbs 1.43 kilojoules of heat, its temperature increases from 24 degrees Celsius to 39.1 degrees Celsius. Determine the specific heat of this metal and predict its identity. Okay, so let's go ahead and try solving this problem. Okay, so again, you sort of have to figure out what formula to use. And so why don't I just go assign as many variables as I can first, and maybe that will sort of point us into the direction as to what formula we use to solve the problem. So it says first, a piece of unknown metal weighs 254 grams. So that sounds like a mass, right? So mass is equal to 254 grams, okay? And then it says when the metal piece absorbs 1.43 kilojoules of heat. Okay, so it's absorbing heat, and you're given the value of heat it's absorbing. The symbol for heat is Q. So this is Q, and this is 1.43 kilojoules. And just a note, this is not the typical unit you would use with these kinds of problems. You usually have to be in joules. So we might expect that we'll have to convert kilojoules into joules. Okay. What other information do we have? It looks like we have a temperature change. We're going from 24.5 degrees to 39.1 degrees Celsius. So delta T is going to be T final minus T initial. It looks like it's going from 24.5 to 39.1. So the final temperature is 39.1 minus the initial temperature, which is 24.5. And so if we go ahead and do that, as I recall, this temperature change is going to be 14.6 degrees Celsius. Okay. All right. So it says determine the specific heat of this metal and predict its density. So if they're wanting a specific heat, they basically want a specific heat capacity. So you may recall that that is symbolized by a small letter c. So here we're given mass, we're given heat, we're given the temperature change. This time we had to find the specific heat capacity, which is little c. So what you have to do is recall the formula for that. So hopefully you'll remember for the test is that little c, the specific heat capacity, is equal to Q over m times delta T. Okay, so we're trying to solve for C, so all we need to do is plug in Q and then mass and delta T and just do the math, and we should be able to get a value for C. So let's just go ahead and do that. So C is going to be equal to Q. Now be careful. We ask ourselves, if for Q, can it be in kilojoules? And you have to be careful about this. The answer is no, and the reason is this. I need a little bit more room here. You sort of have to think of the typical units that C is going to be in. So the typical units we should end up with are going to be joules per gram degrees Celsius. So it's not kilojoules per gram degrees Celsius, it's joules. So before we plug it into this equation here, such that we can get joules per gram degrees Celsius, you must convert this kilojoules to joules. Okay, so let's go ahead and do that. So it's going to be times 1,000 joules over 1 kilojoule. And so this is going to be 1,430 joules. Okay, now I think we can go ahead and plug things in. So C is equal to 1,430 joules divided by the mass, which is 254 grams, times the temperature change, which is 14.6 degrees Celsius. Okay, so I think if you went ahead and did this math, you would get that answer on the screen there, which is 0.386 joules per gram degree Celsius. Okay, so the final part of the question is you have to identify the kind of matter this is. And so maybe one of the things you might remember is that the wonderful thing about a value of specific heat capacity is it tells you the kind of matter it is, and the reason is all different kinds of matter have their unique specific heat capacities. So in order to figure out the kind of matter this is, we would need a table of specific heat capacities, and we would have to look up in that table what kind of matter has this specific heat capacity of 0.386 joules per gram degree Celsius. And in fact, there is a table there, and you can sort of look through it, and what you'll see is that of the different kinds of matter listed, it is copper that has very close to the specific heat. So here, probably what the matter is in this case is copper. Okay, thank you for listening. We'll see you next time.